When cold fluid enters a hot pipe, it doesn't heat up uniformly all at once. The fluid moving through the center of the pipe remains completely unaware of the hot walls around it during those first few moments. Looking at this diagram of fluid entering a tube, you can see exactly how the process begins. The fluid at temperature T sub I hits the wall, and the heating effect starts at the pipe edges, slowly creeping inward toward the center line. This initial section of the pipe is called the thermal entrance region. The specific zone where the fluid is actively changing temperature and building up heat is defined as the thermal boundary layer. Because that boundary layer grows thicker as the fluid moves downstream, there is a specific physical distance required for the top and bottom layers to finally intersect in the center of the pipe. That exact distance is the thermal entry length, labeled here as L sub T. Understanding this creeping heating phase is critical. The behavior of the fluid in this specific zone dictates how effectively the entire pipe system transfers heat overall. Moving to the right half of this diagram, labeled the thermally fully developed region, we analyze what happens immediately after those boundary layers meet. It's easy to assume the fluid stops heating up. It doesn't. The fluid continues to gain heat, but the relative shape of its temperature profile remains uniform. The mathematical rule defining this is that the ratio of surface temperature differences locks into place and remains perfectly constant. This graph maps how the growing boundary layer physically impacts the system's convection heat transfer coefficient, H sub x, along the pipe. At the exact entrance, the boundary layer is paper thin. It provides almost no thermal resistance, resulting in a massive initial spike in the heat transfer coefficient. But as that boundary layer thickens downstream, it acts like an insulating blanket. The coefficient drops steadily until the flow becomes fully developed, at which point H sub x stabilizes into a flat, predictable line. Calculating the entry length, therefore, is about finding the exact coordinate where the system's heat transfer efficiency stops fluctuating and settles into a constant value. To find that exact coordinate, we have to look at the physical state of the flow. Whether the fluid is moving neatly or chaotically completely changes our math. In laminar flow, the fluid moves in neat parallel layers. Heat must slowly transfer across these layers via molecular diffusion. Because this diffusion is slow, the required entry length depends heavily on the fluid's speed, the Reynolds number, and its specific thermal properties, the Prandtl number. Compare that to turbulent flow. Here, intense mixing smashes the fluid layers together. This chaotic motion transfers heat rapidly, completely overpowering the slow process of molecular diffusion. Given that this turbulent mixing happens incredibly fast, pause the video and try to guess the entry length formula for a standard 5 centimeter water pipe. The rapid mixing is so dominant that engineers can safely use a shortcut. For most practical calculations, we assume turbulent flow is thermally fully developed after just 10 pipe diameters. The Reynolds and Prandtl numbers become essentially irrelevant for this distance. The physical behavior happening inside the pipe dictates which mathematical framework you must apply to solve the problem. To see the practical magnitude of this difference, let's look at a side-by-side comparison of thick oil flowing in a laminar state and water flowing in a turbulent state through the exact same pipe. Orderly oil flow has a high Prandtl number. Relying on slow diffusion, it requires a massive distance, over 50 pipe diameters, to fully develop. The turbulent water violently mixes temperature, achieving a fully developed profile at just 10 diameters. Save this visual summary. It maps the physical drop in the convection coefficient against the two required engineering formulas. By identifying your flow state and calculating the proper entry length, you secure the correct heat transfer coefficient, ensuring reliable thermal predictions for the entire system.